Hello, welcome to Electronics Education. This is Vincent Chang. Today we are going to continue our lesson on the practical operational amplifier and focus on the slew rate of IC operational amplifier. This is not a very easy lesson to understand. When I was a college student, I have no idea about what's, probably I only know the definition of the slew rate and nothing else. But in this lecture, I try to, this is the subject of analog integrated circuit. So without going into too much detail, the technical detail, the device, the frequency compensation, etc. But you get the big picture and you get the core concept. So it's a balance between, at this stage, so I will pay attention to the balance for your learning. And the product, this is the big picture, okay? Product information, then you'll see this. I explained the bandwidth, the supply voltage range. Now in the middle, there's a slew rate. 0.5 volt per microsecond. So first, the typical value for the dimension is volt, not per millisecond per second, per microsecond. And the definition, this is actually referring to this one. SR means the slew rate. It means the maximum value of the output slope. The maximum value of the rate of the output change. The maximum rate of change for the output voltage. Maximum rate of change for output voltage. But how to measure this? Just assuming if you get an operational amplifier and you go to the lab, now how are you going to test this? How are you going to measure the slew rate? So you can actually form or you can just get the chip of the short circuit is the on-chip, the follower circuit, the voltage follower. And then you drive the circuit with a large signal step. Not a small signal, but a large signal step input. And see what happened to the output. If you drive a step input, a large signal, what do you mean by large signal? If the supply voltage is 15 volt, then the large signal could be 5 volt, could be 3 volt. That's big enough. Something must happen, right? Something must happen. And what happened? If it's the large signal, do you understand what I'm trying to say? I was trying to send you a signal. Think about this. If it's 5 volt, what's the gain of if the amplifier in the linear region? The linear region I was talking about in the previous lecture. 100,000, right? So if it's 5 volt, then in the linear region, how big the output voltage is going to be? 500,000 volt? That's ridiculous. That's ridiculous. So something must happen. I don't know, something must happen. What happened? But I do know this. Know this first. It's going to become a linear, it's going to be a ramp. It's going to be a linear ramp. And that ramp, the slope of that ramp is defined as the slew rate. That's the limitation. That's the large signal limitation. That's called slew rate. So now, I'm going to try to help you understand more. I can end this lecture here, right? What did you learn? What did you learn? You only know the definition of the slew rate and know how to read the data and know waveforms, large step, and ramp. What else? There's no insight if I am here. So I want to give you the insight, but also searching for a balance without going too much detail. I know some of you might not have the foundation on the semiconductor device, right? You don't know about the operating principle of, not to mention what other topics. So I know your background. So with limited backgrounds, how I can give you some insight of the slew-rate? I still can. As long as we adopt a simplified op-amp model we talked about before. So remember this? Remember this? I explained this before. Red, blue, and orange. Input stage, gain stage, and output stage. That's the simplified op-amp model. The first stage, the gain stage, the GM represent is the input differential transconductance amplifier. The transconductance means when current divided by voltage is a conductance, but it's the output current of the first stage divided by the input voltage of the first stage. So it's the current there divided by the voltage here. So it's a transfer. So it's transconductance denoted by GM1. The transconductance of the first stage. A2. The gain that the second stage provides. And the CC, I explained this, I introduced this before. I didn't explain, but I introduced. It's called compensation capacitor. And the last stage, you can simply assume it's the unit gain buffer. It's the unit gain buffer. So now, since we talk about a follower, a voltage follower, so there's a feedback connected between the output and the inverting input. So let's do this later, all right? Let's do this feedback later. But now, I want to know a little bit more about the model. This is actually what I just talked about, the characteristic of the first stage. I said the transconductance means the relationship between the output current, which is I01 of the first stage, and the input differential voltage of the op-amp. So VID times GM1 becomes a current, right? So the GM, the transconductance, is actually the slope of this transfer characteristic of the first stage. So it's the input stage transfer characteristic. So similar to the concept I introduced in the previous lecture, this one also exists linear region in the middle and the saturation on both sides. So when it enters into the saturation region, so it becomes natural, right? So now you know why I need to teach you the transfer characteristic first before I dive in to this one. So I capital M represent the saturation current of the differential amplifier. The maximum current that the differential amplifier can provide. And also the I lowercase m is another limit. All right? So now let me start to explain the inside of the slew-rate. I said this is the open circuit. So now it's a follower, so let's connect the feedback, the blue line. The blue line, and then feed the follower with a large step input. Because when large signal, large means what? Means it's not tiny, it's not small signal. Now what do you mean by the small? The small means the amplifier is operated within the linear region. The linear relationship work. So large means what? Exceed the limit of the linear region and enter into the saturation region, right? So when the amplifier saturate, what amplify? Wait. What amplify? The input differential amplifier saturates. Then what current can he provide? What current can the differential amplify? That's all I have, right? I give you all. I give you all I have. The maximum current is all I have. That's all I have. You got it? So now, because the gain is huge, we can, in reality, the A2, the typical value is around 500. But we can assume it's infinite, it's huge. So that means the voltage at the input terminal of the second stage can be assumed as virtual grounded. VG represents the virtual grounded, the virtual ground. So then the VO becomes what? Becomes VO2, the virtual ground. So becomes the capacitor voltage. So what kind of output waveform in this condition will show up? What kind of output waveform? So now it's your turn. I want to pause and answer this question. To analyze this situation, I think 1 minute is long enough. 1 minute. So let's pause for 1 minute. I'll be back. Are you struggling? Because of the capacitor, you kind of get stuck when you see the capacitor. I told you this before, right? The red highlight. You don't need a very high level negative theory before you can solve the capacitor in the time domain. You just need very basic one. You just need the very basic one. This one, dq equals I dt equals C times dV. I times dt equals C times dV. This is good enough. What I? This I. What V? VO. That's it. That's it. So it tells you the derivative of the VO is the constant. When derivative of a variable is a constant, so what kind of function in the time domain? What kind of function you got in the time domain? It's a straight line, right? It's a straight line. And then the slope is proportional to why I use the variable capital M. I just try to give you a signal that that's all I have. So that slope, that the current is all you have. So the slope is the limit. Is the limit I can offer. So that limit is called the slew rate. You got it? Here's the takeaway, the slew rate limitation. So you understand for a follower, starting with the follower, and the follower is fed by a large signal step input. Large means the saturation region. It can be it's not in the linear region anymore. And then we use this model for internally compensated IC op-amp. We know there will be a maximum current or I have current flowing through a compensating capacitor. So based on the I times dt equals C times dV, it tells us dVO dt, the slope will be a constant. It tells us it's going to be a linear ramp. And that the slope of that ramp is the maximum slope, rate of change, when large signal is present. It's the maximum rate of change when large signal is present. That's the key message you need to get from this lecture. So in the next lecture video, I'm going to explain to make the link between the slew rate and the so-called full power bandwidth. See you there. Thanks for watching.